Oh, plug back in so we don't kill it. All right, my friends. Kurt had a great point. He said, looking back to the impurity problem of the pond impurity, if we're looking at removing 70% each hour as it goes by, we're obviously removing less each hour as it goes by. It's the same percentage, but it's less and less of an amount each time. Obviously, from 0 to 1 hour, we remove 70%, which roughly equates to 0.7. Then we went from 0.3 to 0.09, which equates to I can't do this in my head right now, 0.21. Then we went from 0.09 to 0.27, which drops down again. So basically, you're removing less and less each time. Same percentage, less overall amount. And that's really the difference. You guys nailed this before. That's the difference between an exponential model and a quadratic model. A quadratic model has a constant second difference, whereas the exponential has a constant first product, multiplication versus subtraction, if that makes sense. Rather than taking the same amount away each time, you're taking the same percentage away each time. So that's the big, and I say taking away only from the decay model. We'll get into the growth model here in a second. We'll use student deck to talk about that. So anyway, let's answer the question. Let's answer the question. The question is, how long do we have to wait until we're down to less than 1%? Well, we know that the model is now 0.3 to the x, where y is the percent remaining, and x is the number of hours. And Kurt said, man, do we have to just keep doing this until we get down to 1? Well, you can. You can just keep going, 0.7 away, 0.7 away, times 0.3, times 0.3, times. Or you can use technology to assist you, which is kind of the point. I mean, it's kind of the point is to, once you see the pattern, you're like, oh, and this pattern, of course, is going to continue. Because you're going to keep multiplying by 0.3, by 30%, by 30%, by 30%. So let's use it to help us out. Let's use it to help us out. Get them fired up, get your model in your TI. OSHA ever comes in here and sees what this looks like. Good Lord. Broken noses aplenty. Let's go, actually I'm going to go right here, if it's okay with you guys. I'll just clear this. Make sure we can see this okay. That's not bad. All right, shall we? Y equals, oh, look at that, gorgeous. If you have any plots on, turn them off. They're going to get in the way. We can plot the data if you want. If you guys want to, we can actually plot the data points 0, 1, 1.3, 2, 0.09. Do you want to? Want to make a scatter plot? We don't have to. We don't have to. The reason why you make a scatter plot usually is because you're trying to see the pattern. We know what the pattern is, so it almost seems superfluous. What the hell? Let's not do it. Let's not do it. You know how. You know how to do it. Let's just get the equation in. 0.3 to the x power. Right? That's all the equation is. I mean, you can put a 1 times it, but there's no need to. So 0.3 to the x power is what's remaining. Y equals. Yes. Now, I know we haven't had to go to the screen very often because when we do our regressions, we usually just do like linreg y1, quadreg y1, then you press graph. Remember that y1 is where everything's being dumped to. So we're actually doing our own equation here. We're going to do our own equation. Go ahead and press graph. Here's what I get. I don't know about you guys. That's what I get. Well, there's something there. It's just I'm looking in the wrong place. No, 0.3 to the x. Oh, okay. 0.3 to the x. This is terrible. Everybody press graph. Everybody press graph. It's crap.
I got it. Oh,
yes, you have a different window than me. I have this, you have that. My window sucks. I don't like it at all. Yeah, that's my window. So I got an idea. Let's recant my previous statement, and let's put some points and make a scatter plot. Because then, if we use some points and make a scatter plot, what cool little trick can we use to get a good window? That zoom 9 thing. Remember that zoom 9, that zoom stat? Let's put some points in. Let's turn the scatter plot on. Let's go into our lists. What do I got in here? I can't erase all this stuff. That was the number of texts my 243 class sent yesterday. I'm gonna erase that. I need it right now. So let's plot a couple points. 0 and 1. 1 and 0.3, 2, and you know what? How about 0.3 squared? We can do that. Let the TI do the math for us. 3.3 cubed. 4, what would 4 be? 0.3 to the 4th. You guys know how to do the to the caret? The caret button is your exponent button on your TI. Caret over here by above the vision. We don't have it on our chart. Somebody just said that. We didn't have it on our chart, but isn't the pattern going to continue, friends? The pattern's going to continue. You can actually, Matt, say that again. You can actually do mathematical expressions in the actual lists themselves. Yeah, which is kind of sweet. Kind of sweet. You can also, this is kind of freakish. Watch this. Suppose I got the 5 and 6. What I can do, if you want to see this, stop by after class and I'll show you how to do it. I can actually put an equation in L2, and I can say up there, take what I've got in Y1 and apply it to all the elements in L1. When I press enter, it fills them all up. So that, I mean, it acts like a spreadsheet in that way. If you guys care to see how to do that, just stop by after class and I'll show you. It's one of those things that comes in handy, like kind of, sort of, sometimes, but probably not worth memorizing if you're not going to use this more than just in 105. But I just did that. You don't have, I think 4 is enough, Maddie. I mean, I just did it to prove the point. You probably stop at 4. Okay, so we got 5 points. Go turn the scatter plot on, friends. Go turn the scatter plot on and go look for them. So, yeah. I'm going to go kind of quick only because you guys know how to do this already. Was that a snicker back there? John, you know how to do this. And what you have, and if you don't, what do you have to help you? Your magic little booklet. Don't lose that. Your little booklet. Yeah, you're going to want that too. It's a gift from me to you. Use it in good health. Or poor health. Just use it in general. So here's my plot screen. And then the whole reason we did this scatter plot was to use what command? Zoom 9. Zoom 9. Get there. Look at that. There it is. So when I pressed graph last time, I was seeing that curve, but I was seeing it somewhere else, like far away. It was way over there or something. I don't even know where the hell it was, but it wasn't here. Cool? So, we need to answer the question. How long do we have to wait until we're down to 1% of the impurities? How are we going to answer that? What is that 1%? Is that an X value or a Y value, friends? Is that an X value or is that a Y value? Do you remember? It's got to be, doesn't it? We set our model up as X being the number of hours and Y being the amount remaining. So we need to find X when Y is 1%. So essentially, you have to solve this equation. 0.01 equals 0.3 to the X. How do you think we should do this? Think back now. Think back to about a week and a half ago. When you have an X value and you're looking for a Y value, I know that's not what's going on right here. But when you have an X and you go for a Y, which tool do you use on your TI? Second trace is for when you have a Y and need an X. Okay. I'm saying it backwards, and I apologize, it's a little confusing. No. If I gave you an X value, suppose I said, after 10 hours, what percent impurity would be left? Where would you go to solve that? Your table. You'd go second graph, and you'd plug in the X value, and the table would kick out the Y value. What if you have a Y value and you need the X value? You go to second trace and you intersect. We have to graph the 1%. Go ahead, go. Let's solve that in a second. Hang on 1 second. Let's go back to our Y equals. Put a 0.01%, 0.01, which is 1% in there for Y2. Now watch. Press graph again. You're not going to see a great deal of difference. You see it down there? That was 1%. Did you see it come across? Let me do it again in case you missed it. It is tiny because what you're looking at is this is 100%. So that's 50, 25, 12 and a half, 6, and so forth and so on. It's got to be pretty small. So I'm going to turn this guy back on. Here they come. There's your curve. That's 100% dropping. Here comes 1%. Right there. And somewhere, that guy is going to touch that guy. That's when we've hit 1%. Whatever the x value is of that is when we've hit 1%. Our job is to go find that. Our job is to go find that. I propose we play with our window a little bit. Do we need to be looking back here at 0 hours and 1 hour and 2? No, it's happening obviously past that, right? So I propose we go to our window screen. We go to our window screen. And we start the x-min. We know it's past 3 hours, right? Why don't we start our x-min at 3 hours and go out to something like 10 hours? Let's see if it happens somewhere between 3 and 10 hours. Is that fair? So that's the time. Now let's play with our y's. What should we set our y range to? Remember, we're looking for 1%. Does y max have to be at 1.16? That seems a little excessive, doesn't it? Cindy, what do you think? Give me a good y top. What do you think?
0.05.
Love it! 5% is perfect. I love that. 0.05. That's going to show 5%. And then we're going to have to pass through 1%. So what do you think a good y min would be? Give me something under 1%. What's a pretty logical one? 0. I'm not saying we're going to equal 0. I'm saying that's going to be the lowest part our window is looking at. So now instead of going from 0 to 100%, we're looking at 0 to 5%, which is going to make a lot more sense because we're going to be seeing only the stuff we're interested in. You ready? Let's press graph now. There it is, there it is, there it is. Where's 1%? Boom! Right there. Right there. Say that again? Yeah, hit graph. You don't want to press zoom stat. If you press zoom stat, the problem with that is it's going to go back to that original window that you had. As soon as you start messing with your window button, start pressing graph. And again, I apologize if some of this window trace stuff is going by a little quickly. I forget who had whom for 95. At 95, you learn all this stuff. And like I said, when I do 95, I do so much TI work. And yeah, so we'll slow down and we'll pick up stuff as we need. Go ahead, Cheryl.
Can you go back to window again?
Of course.
See what you have there.
Of course. I just set it from 3 to 10. So 3 hours after we started and 10 hours, 10 hours. And then Sydney had a great idea. Because we're looking for 1% on the y's, we just go from 0 to 0.05. 1%'s between there. And the reason we like that is because it actually brings it up a little bit. If you want to make it even more extreme, more extremely obvious, change the 5% to 2%. That'll put 0.01 right in the middle of the screen, right? Not that your 0.05 wasn't great, Cindy, it was. But if you make it 0.02, you'll see the 0.01 come right across the middle. Fair? Here we go. Graph. There's that last little point right there. 0.01's going to come right across the middle. Shoo, right there. That's the time. Whatever this is right here is the time that we're down to exactly 1%. Our job, go find it. Second trace. This is where your intersect is, Kurt. You got it, my friend. Intersect. Yes, I would like to use y1 as my first equation. Enter. Yes, I would like to use y2 as my second equation. Enter. Guess. I don't care. You're the TI. Figure it out. Boom! We got to wait roughly 4 hours. 4 hours will do it. 4 hours will do it. That'll get us down to 1%. Now, it's 3.8, but that gets us right to 1%. Round up to 4. Make it simple. Make it simple. 4 hours will get you down to 1%. There you go. Does that make sense? Is that fair-ish? Fair-ish. So this is the beauty of technology. You want to use technology. For sure you want to use technology. It's your friend. But you also want to know what the hell the pattern is underlying it as to why the technology is there. Is that fair-ish? Yeah. Let's look at one more. Yeah, this is perfect. We can check it a little bit earlier today if you want. This is all great because this is exponential decay. This is exponential decay. This is when we're removing percentages from quantities. So somebody said half-lives. Carbon-14 was a good example. Who said carbon-14? Echo, that was you. Carbon-14, what they do is they measure how much carbon-14 is left in something that used to be alive or used to be organic and is now dead or rotting away. And by figuring out how much carbon-14 is left compared to how much was in it originally, they get a percentage. And that percentage based off the half-life of carbon-14, which is something like, I want to make up a number, 4,000 years. Every 4,000 years you lose half of your carbon once you die or stop producing it. You can reverse engineer how old something is. But that's still a decay model. You start with 100% of your carbon-14, and after 4,000 years you're down to half of it. And after 4,000 more years, you're down to half of it again, and half of it again, and half of it again. So that's the idea of carbon dating. It's still an example of decay. So what we'd like to look at is an example of exponential growth. Just one example of this should do the trick pretty nicely. One example of this should do the trick pretty nicely. And that's when your b value is actually bigger than 1. That's when your b value is bigger than 1. So it's still going to look the same. A times b to the x. But now the b is going to be more than 1. I'll give you a real quick example. U.S. population. This is an interesting one.
Is that the other if?
If.
You said there were 2 ifs earlier in the lecture today.
2 ifs.
Yes.
What did I say?
The other was the exponential decay.
Right, so there's decay and growth, yes. There's two branches to this model. So it all depends on how big this number is compared to 1. If it's less than 1 and still positive, we're decaying as time goes on. If it's bigger than 1, we're growing as time goes on. So here's an example. This is a really, really nice model to talk about the rate of change of growth in the United States. The United States population growth is just about 1% per year. That's roughly how fast the population of the United States grows. It doesn't grow like by 300,000 people per year or by 500,000 people per year. It grows by roughly 1% per year. Now, why would that make sense? Why would exponential growth of like a thing like the United States make sense? Why do you think, rather than quadruple? Why don't we just keep adding the same number of people every year to the United States? Why doesn't that make sense? What do you think, Gabe?
Because if you're adding more people, then aren't you? Oh, it sounded great in my head. I don't know how to explain it.
That's okay, man.
Like,
Sounds great to my ears.
It's like you're adding more people, so that's more, I guess.
I think I know where you're going with this. Let me come back to it. Sydney, go ahead, give me your idea.
Because people die every year.
Oh, good. You're talking about overall change. Good. People die every 7 seconds or something like that, right? Every 10 seconds or something. But then somebody's born every like 7. And I think the birth is slightly faster than the death, which kind of makes sense as far as growth. So that's quite good. I wasn't considering that. Very nice. I'm looking at net change, I guess. Cheryl, what are you thinking? Are you going to say the same thing? So you guys are looking at net overall change, deaths and births adding up. What I'm telling you is that average is 1%. I was thinking of something a little more lewd. Essentially, if you add, let's say you add 300,000 people every year to the United States. So this year, let's make up a number. This year, there are 1 million people in the United States. I know that's too small, but to make the math easy. Next year, there are 300,000 more, so now it's 1.3 million.
Right.
Year after that, 300,000 more, 1.6 million. Year after that, 300,000 more, 1.9 million, and so forth and so on and so forth. Here's the problem I have with that. When we add new people to the U.S., how do you think most of them are added to the U.S.? How do you think? From births, right? I mean, there are some immigrations in, and then immigrations out, and there are deaths. But I'm guessing the vast majority of the increase of the population is due to birth. Think about how births happen. 2 become 3, 50% more. Or 2 become 4 if you have twins or triplets, but that's a rare case. Look at the single births. It's a multiplication, not an addition. 2 become 1, so it increases by 50% in each of those little pairs. So it's more multiplicative than additive if you view it that way. And that's why I think this makes sense, that it's an exponential model. And if you look at the data, it's perfect. So what would that equation look like? What would the equation for the United States population look like? And why would you even care in the first place? Who the hell cares if you can model it with an equation? Who cares?
It would be.
I care. You should care too. Why do we care about this? What's in the news all the time? Water usage, resource usage, Social Security, all these things. We are stretching our resources so thin in this world, let alone this country too. We should care about the growth of this country. We should care about how big it's getting. So let's make up a number again. Actually, I don't have to make it up. I have it written down. In 1915, there were 100 million people in this country. In 1915, there were 100 million people in the U.S. Yeah, according to the U.S. Census Bureau. Okay, U.S. Census Bureau. 1915. According to that, and the fact that we're growing at 1% a year, can you give me an equation, y equals something, where y is the population of the U.S. in millions, y is the population of the U.S. in millions, and x is the number of years, I know this is thrilling, since 1915. Can you give me an equation based on that? Say yes.
Yes.
Yes, because you can. You've got everything you need. You've got everything you need, friends. You've got everything you need right here. Ray, what are you thinking? What are you thinking?
I'm thinking it's y equals, would be 100 million.
Even simpler, just 100.
Just 100.
Because I've defined the value to be in millions.
Okay.
Go, Renee, 100.
100 times 0.01 to the x.
Awesome. I'm going to add one number in there.
1 minus.
1.0. Actually, 1 plus 0.01. Here's why. I'm going to write an equation, then I'm going to blow it out like I did earlier. 1.01x. Now, Renee's got all the components we need, all right there. But I want to blow out this model like I did with the coin flip. I've now erased it with the coin flip model. The reason why it's 1.01. Remember with the coin flips, it was 1 minus something because we were taking away 52% on each flip. We're not taking away anymore. We're adding 1% each year. So this bad boy right here is kind of like this. Y equals 100 times 1 plus 0.01 to the x power. Yeah, does that make sense? Yeah. That's the difference between exponential growth and exponential decay, is the plus sign versus the minus sign. If it's a minus sign, you're taking away a percentage each iteration. Can I use iteration now? Is that okay? It is a plus sign, but make it bigger.
It looked like it.
Looks like a cross now, damn it.
That's okay.
That looks like an L, damn it. Big L, oh, you're getting the point. So, the difference between exponential growth and decay is in which symbol. There's always a 1. There's always a 1 even when you don't see it in the equation. Like that filter one over there, the 0.3 to the x. There's still a 1, it's 1 minus 0.7. You write it as 0.3 because it's easier. The 1, yes, it's an understood 1. It's the 100% that started there. So the 1 that's here in 1916, if you will, would be the 100 million people from 1915, and we're going to add to that 1% of that 100 million, and that gives us our population in 1916. And whatever that is, we're going to take 1% of that and add it to itself to get 1917. And whatever that is, we're going to recursively keep adding 1% year after year after year. Now what we can do is, I have a couple questions for you. First of all, when did the population of the U.S. double?
100 years.
When did it double? That's the quick and easy answer, isn't it?
Yeah, well.
The quick and easy answer is 100 years because every year it picks up what?
1%.
But here's the problem.
It's 1%, 1%.
It's 1% of 1%. You can't just add up the 1% and say 100% is 100 years later because the base keeps getting bigger every year. So when did it double?
50 years.
How you know? Let's throw that out there. 50, 40, pie, blue,
50 years.
purple. Hey, do we have the tools to answer this? Hell yeah, we do. Let's grab it and look. I'm asking you the same question I did before. I said, how long will it take until we get down to 1%? I'm asking you, how long will it take until that turns into 200? So what I want to know is, if I want to know how long it's going to double, how long does it get from 100 to 200? So I want this to be 2. Let's go to the machines. This is why we have technology, friends. Purple. My new favorite answer for everything. Purple. So turn your plot. We don't need the plot anymore. Plot's not necessary. The plot, remember, is simply a tool to let us see the shape. We know this thing's exponential because I've analyzed the data for you. The data spreadsheet is actually really freaking cool. It's almost perfectly exponential. Let's put the growth equation that Renee so kindly gave us in Y1, 1.01 to the x. Is everybody finding the caret button and the x button and everything? And we're happy? Well, okay, we're content. We're content getting what we need. Happy's subjective in a math class. Cool? And then what's going to go in y2, friends? Absolutely. 200 is going to go in y2. 200 is going to go in y2. Yeah. Because my question was, when does the U.S. population double? When does it double? It was 100 million in 1915. When did it double to 200 million? Is that fair? And we can ask and answer this question at any point if we just adjust the initial amount from 1 to 2. It doesn't matter if it's 100 or 200. It just basically, it's going to double every this long. Come back to that in a second. Graph? Gotta adjust the window. Gotta adjust the window, right? Gotta adjust the window. So, let's use some context. There's no scatter plot. We can't rely on Zoom data anymore. So, go right to your window. Help me design a good viewing window for this, based on what we know and what we want to see. Let me hear some ideas. This is all I did in 95. You guys didn't do this like all the time in 95? Like, I'm getting a blank screen. What should the window be?
No.
Oh, shit. It's like the best part. It's the best part. Like, okay, so for example, what Y